resonance and molecular orbital theory. Alright, so we've discussed resonance before. Molecular orbital theory helps explain it a little better. Can help explain. So say we see this formic acid. Right, we've seen this resonance structure before. The negative charge can start forming a double bond, breaking this bond to give us a negative charge on the other oxygen, and the other oxygen forming the double bond now. This is resonance. Why is this oxygen able to donate its electrons to the carbon and shift negative charge onto the other oxygen? Well, if we look at the orbitals, the atomic orbitals, we have a p orbital and a p orbital on the oxygen and the carbon. This is forming a pi bond, and we have an oxygen sitting out with some electrons in its p orbital with a negative charge. And we'll give them color once again to get a better idea of what's going on. So we have these guys forming a bond, and then we have one negative charge hanging out over here. Those electrons can shift towards this orbital, breaking the pi bond present, but obviously forming a new pi bond. So end up with previous color scheme. Now we have one green guy and two red guys forming the double bond that we see up here. All right, we are observing the negative charge, or the electrons, shifting between all three p orbitals, or as you would say, the pi orbitals. This makes pi bonding crucial for resonance. In other words, you will not see resonance if there is no pi bonding. So we refer to pi bonds that are able to resonate / shift charge between them as conjugated. So when we have, say, two double bonds next to each other, what this is two pi bonds all next to each other. This means that the electrons are able to shift between all of these p orbitals. So this is conjugated. Whilst, say, something like this double bond with an sp3 carbon in between does not allow for resonance or conjugation, because there is no way that these electrons can get to this p orbital or vice versa. Therefore, this is not conjugated. So, an important point though, on lone pairs, on nitrogen and oxygen, amongst others. Can't forget sulfur, phosphorus, some of the halogens in certain situations. The lone pairs are in p orbitals. So they are able to resonate. What do we mean by that? Well, say you have an alcohol and a double bond here. Because those oxygens on those lone pairs, electrons in the lone pairs are in a p orbital, at least one of them is, we could say that that oxygen is able to donate its electrons into those p orbitals. Alright, so just to emphasize, put some color on it. We have our double bond, pi bond, and the electrons on the oxygen, say one lone pair, not both of them, just one, is able to donate its electrons into the pi bond, and therefore we can get resonance. What does it look like? Well, let's have a gander. Those resonate, we end up with something reminiscent of this, where we now have oxygen without any, with one lone pair that is out of the way, it's trigonal planar, and a carbon with a double bond here, and a negative charge on the carbon. Now, how many electron domains does carbon have? 4, but one of them is a negative charge and doesn't have a double bond anymore. So that negative charge must be found in a p orbital that was originally in the pi orbital. So what does that look like? Well, my guess, as good as any, is we now have our p orbitals and one negative charge in that p orbital. Now, of course, it can resonate back to reform what we were seeing earlier. But I've got a little ahead of myself. Main point was this is conjugated because the lone pair is conjugated to the double bond.